This is the Unit 1 Test 1 review recording. This test covers lessons 1 through 4 from our Canvas course. The first topic we're going to review is on simplifying radicals. And here are some tips on how to do that. Perfect squares are the numbers that we really like to find, and perfect squares can be simplified easily. They are numbers like 4, 9, 16, 25, etc. And if you ever have an even power underneath the radical sign, those can be simplified very easily as well. You just take out half of that power. So let's do an example. The square root of 25c to the 4th power. Let's go ahead and break this down. The square root of 25c to the 4th power can be rewritten and split up anytime that I have two things being multiplied under a radical. I can just write that as a product under two separate radicals. And now we're going to see if anything works out really nicely. The square root of 25 is 5. And then c to the 4th power, let me go ahead and expand that out so that you can see what that looks like. So it's c times c times c times c. And anytime you have a term with a partner, a like partner up underneath the radical, that means that that has a square root. So c times c is going to have a square root of c. And then again right here, c times c will have another square root of c. So I'm going to be able to bring out a c from the first pair and a c from the second pair. And I still have my 5 that I started with. And when I simplify it all the way down, I'm going to have 5, and then c times c can be simplified as c to the 2nd power. So that would be our final answer. And that's what I was saying about even powers. I started with an even power of 4 underneath the root, and when I simplified out, I end up with half of that power outside the radical sign. Let's try one more. Let's simplify one that does not have any variables in it, the square root of 20. Now, if I were to plug that into my calculator, I get a really ugly answer. The square root of 20 is not a perfect square, so instead we're just going to rewrite it to contain a perfect square factor. I know that 20 can be written as 10 times 2, or 4 times 5, or 20 times 1. Only one of those options contains a perfect square, and it's the 4 times 5. So I'm going to rewrite this as the square root of 4 times the square root of 5. And when I do that, I know that the square root of 4 works out really nicely to just be 2. And then I still have the square root of 5. Can't do anything with it. It does not simplify any further. So my final answer would just be 2 square roots of 5, or 2 times the square root of 5. When I combine radicals, that's when I'm doing an operation on a radical, and there are two different ways we can do that. We can multiply, which means that we multiply coefficients with coefficients, so your outsides with outsides, and then we multiply radicands with radicands, insides with insides. And you should always simplify when you can. Let's do an example of just that first. The square root of 5 times the square root of 50. I don't see any coefficients in this problem that would be a number out to the front of each radical sign, but I do have numbers inside, so I can just multiply them together. 5 times 50 gives me 250. And then I want to rewrite that to find a perfect square factor so I can simplify it down just a little bit more. 250, let's see, there's lots of ways we can do that. Let's do 25 times 10 because I know that that one will work out. The 25 will work out. So this is equal to the square root of 25 times the square root of 10. And I know that the square root of 25 is just a plain old 5, no more root. And then the square root of 10 can't be simplified any further, so I am finished. This would be my final answer. When I'm adding or subtracting radical signs, that's what makes it a little bit trickier because sometimes you have to manipulate the problem before you can actually work with it. We need to make sure that the radicands are alike. They must match each other. Then we can add or subtract their coefficients. So let's try this problem right here. When I look at the problem, I see that my radicands do not match. 27 does not match the 3. I need them to match before I can do the actual subtraction that this problem is asking me to do. So what we're going to start with is see which way we want to simplify. The square root of 3 cannot be broken down or simplified in any way, so I know I'm going to be stuck with that thing. I'm going to be stuck with the square root of 3 in my problem. So if I can force the square root of 27 to contain a 3, that's going to be my best bet at simplifying. Well, I know that 27 is equal to 9 times 3. That would give me a 3. So let's try rewriting it that way. So this is equal to 5 times the square root of 9 times the square root of 3. And I'm going to be subtracting 17 square roots of 3. The square root of 9 works out really nicely. That's a perfect square. So it works out to just be a plain old 3, no more root. And I'm multiplying that times that square root of 3 that I could not change. Subtract 17 square roots of 3. Now I'm going to simplify what I can. This 5 times 3 out in the front, they're both coefficients. I can just multiply them together. They make 15. And then everything else stays the same. And now that my radicands match, I have a square root of 3 in both terms. Now I can subtract them. So I'm really going to take the 15 and subtract 17 to get my brand new coefficient. And when I do that, I get -2. And then the square root of 3 stays. I don't change it. I just leave it alone. All I did on this last one was I added the two coefficients or subtracted the two coefficients from each other. 15 minus 17 gave me the -2. Variables in an expression always represent something that is unknown. And if your variable is repeated or used over and over again in a problem, it's going to represent the same thing everywhere in that problem. So if you're using x twice in a problem, it's going to stand for the same thing both times. Coefficients are numbers that we multiply with variables. They stand up in the front usually. And then constants are numbers that don't change. They stand by themselves and are not attached to any variables at all. When we simplify an expression, we have to remember that we can only combine terms that are alike. And the way you know if they're alike is if they have the same variable or not. So let's try simplifying this expression. I'm going to color code the terms that are alike and simplify them piece by piece. So I see a 3y. I'm going to underline that in red and look for anything else that has that variable. I see a plus 1y right here. So let me go ahead while I've got my red pen and just do that step. 3y plus one more y gives me a total of 4y. And I'm going to move on to the next piece. Let's do the x's because that's what I see next. I see plus 5x and minus 2x. That would give me a total of positive 3x's. So I'm going to write plus 3x. And then the very last piece are my constants. I see a minus 4 and a plus 8. -4 plus 8 gives me positive 4. So I'm going to write plus 4. It's really hard to see. Let me change colors. We'll make it yellow. I'm going to write plus 4 to finish out the problem. And that would be my final answer down there at the bottom in the 3 different colors. 4y plus 3x plus 4 is my simplified answer. I can't do anything else with it. I can't combine anything else with each other. Let's try actually doing a word problem to write an expression that stands for the situation. Central High School plays Eastern High School in a basketball game. Eastern had double the score of Central before Central scored a three-pointer as the game ended. The variable C represents Central's score before the three-pointer. Express the total points scored in the game as a variable expression. So what the problem is asking us for is not each team's points. What are the total points? Like if I were to add up all the numbers on the scoreboard at the end of the game, I want to know what I would get. The total points that are scored is going to be equal to Central High School's points plus Eastern High School's points. And so I just need to figure out how I can write each of those pieces based off of the information that it gave me in the word problem. So let's go see if we can find Central High School's points. It tells me right here that the variable C represents Central's score before the three-pointer. So I know that they're going to have C points, and then they are going to score a three-pointer. So Central is going to have C points, and then they're going to score an extra 3 points at the end of the game. Now, Eastern High School, it tells me that they had double the score of Central before the three-pointer. So the way that I would write double something is 2 times that amount. So Eastern is going to have 2 times C. C stands for the points before the three-pointer, which is exactly what we want here. And we should always combine any like terms that we see. I have a variable C and then something else with the variable C. When I combine them together, 1C plus 2C equals 3C, and then I have that plus 3 from before that I didn't change. This is our final answer for the total points that were scored in that basketball game. Now, if I want to take that expression and actually do something with it, I can do that too. The total points scored, we said, is 3C plus 3. We jot that down below. And it says if C equals 41, how many points total were scored? So anytime it gives me a value for a variable, I can just plug that in the place of that variable in the problem. So I can take 3 times 41, and then I'm going to be adding 3. I always follow my order of operations, so I'm going to multiply before I add. 3 times 41 is 123, and then when I add 3 more points, I get a total of 126 points in this game. That's from both teams. If I wanted to interpret it piece by piece, I also could. If C is 41, that means that Central High School scored 41 points before their three-pointer. So Central High School scored a total of 44 points. So if you wanted that information, we could do that as well. Central scored 44 points. And then it said that Eastern scored double the term C. So double 41 would be 82. And that would be how the score was broken down at the end of the game. Let's try another one for interpreting pieces of an expression. So in the expression 2 times 10x plus 15y, x represents the number of hours works at a clothing store. I'm going to color code that real quick. So x is the clothing store. And then it says that y represents the number of hours she works in a week as a babysitter. The expression shows how much money Nina has earned this month. Which statement is true? And I just want to go through one by one and see if I can eliminate any answers that seem obviously wrong. So let's take a look at the very first option. Nina has worked a total of X minus Y hours so far this month. If I want the total hours that she works, I would be adding the hours at the store and then the hours of babysitting. I would be adding X plus Y. So working a total of X minus Y does not make sense. The second option says Nina works 15 hours a week at the clothing store. Let's go see if that makes sense. The 15 in the problem is sitting next to the variable Y, and I know that Y stands for how many hours she babysits. So right there, that tells me that that's incorrect. The 15 is not attached to the clothing store. The 15 is attached to babysitting. But also, this option says that 15 is the number of hours. Well, I know that the number of hours is actually my 2 different variables. So 15 is not a variable. That's like another reason why that one would be incorrect. The third option, Nina makes $20x at the clothing store each week. So let's take a look if that makes sense. 20x, let's see where you're getting that. I don't see the number 20 in the problem, but I do see a 2 times 10x, which would simplify to be 20x. And 20x would be a dollar amount times a number of hours. I know that X does stand for the hours at the clothing store, so that one sounds like it could possibly be true. Let's check the last option just in case. Nina makes $10 per hour babysitting each week. I know that babysitting is the variable Y. Let's go see if a 10 is attached to that. I see a 15, not a 10. So I know that that one is also incorrect. We have one best option for an answer right here. When we're doing a unit conversion, there are some simple steps that we need to follow. We're always going to start with whatever the problem gives us, whatever quantity they give us to start with, and write it down as a fraction. Then we're going to multiply by the correct conversion factor by choosing what goes on top and choosing what goes on bottom. What I want is for my unwanted units to disappear. They need to cancel out. To finish off the actual math step, I multiply my fractions straight across. So in this example, how many pounds are in 6 ounces? I'm going to convert the ounces into pounds. I'm going to start with what it gave me, which was 6 ounces, and OZ is the abbreviation for ounces. And it says to write that as a fraction, so you can turn anything into a fraction by putting it over the number 1. And now I'm going to multiply by the correct conversion factor. It says that 16 ounces are equal to 1 pound, so I know that those are going to be my numerator and denominator and my fraction. I just have to choose which one goes on top and which one goes on bottom. I know that I want the ounces to cancel because the question says how many pounds are there. So I don't want the answer in ounces. I want the answer in pounds instead. So to make sure that the ounces will cancel, I'm going to put ounces on the bottom. I'm going to put pounds on top. Don't ask me why LB is the abbreviation for pound. It just is. Now I'm going to go fill in the numbers where they go. 16 ounces is equal to 1 pound. And now if you look, the ounces on top and bottom will cancel with each other, and I multiply fractions straight across. So I have a 6 times 1 on top and a 1 times 16 on bottom. My only unit that's left is pounds, and then I can simplify that answer. It would be 3/8 of a pound. So for this example, we're not actually going to work anything out. I just want to talk real quick about when to round in a problem. This goes for pretty much anything we would do. The Ruiz family is exchanging euros for dollars. The exchange rate is 1 euro equals 1.35261 US dollars. Since the Ruiz family knows that US dollars are stated to the nearest hundredth of a dollar, they use the conversion ratio 1.35 US dollars is equal to 1 euro. Will this give the Ruiz family the correct exchange? Anytime that you round before you do the actual math, it can affect your final answer. So, I mean, you can try one like this if you want to work it out 2 different ways. Just say that you've got 5 euros, okay? If you have 5 euros, that means that you're going to be multiplying 5 times 1.35261. And I'm just going to use my calculator real quick. I should have brought it up on the screen for you. Let me just try and convert 5 euros and see what I get the long way and then the rounded way. So let me write it down for you. So if I do, give me a second to write it out. Rounded, not rounded. When I don't round and I do 5 euros times 1.35261, I'm going to get 6.7305, which would then round to $6. Let me write it like money for you. $6.76. That would be the conversion if I use the entire conversion ratio, the long one. That's what I would get. If I go ahead and round it right away and I convert 5 euros and I do 1.35, let's see what I get that time. I get 6.75 exactly. Okay, so $6.75. So you can see that the answers are different. They're not different by very much. They're only off by a penny. But if they had a larger quantity of money to convert, the answer would be off by a whole lot more. So this just kind of shows you that you shouldn't round until the end of the problem because it could actually affect your answer. So again, I converted 5 euros. Let me write down what I did in case you lost that part. I'm going to convert 5 euros to US dollars. And if they had more than 5 euros, the answer would be off by more than just a penny. Here's something that we didn't quite get to in class, but I want to make sure that we do review this. This should be review from an old math class. When you're dealing with unit conversions that have square or cubic units, your conversion factor might not be what you think it is. So I just wanted to break this down real quick. Let's consider square inches versus a square foot. Anytime you see that word square, it's generally referring to the area of something. So if I want to figure out how many square inches are in a square foot, I can use this diagram to kind of help me break it down. So you can see that 1 foot, that's this length right here. If I have a section, like an area that's 1 foot by 1 foot, let me write that down. 1 foot by 1 foot, that's actually 12 inches by 12 inches. And when I multiply 12 inches by 12 inches, I get 144 square inches. So that tells me that 1 square foot is equal to 144 square inches. It might be very tempting to say that 1 square foot is equal to 12 square inches because you know that there are 12 inches in a foot. But if you look at this diagram, there are a whole lot more than just 12 little squares inside that big picture. There are actually 144 little squares inside that big picture. We can do the same thing with cubic units. Cubic is three-dimensional when we're taking the volume of a figure. And if I have a cubic foot, that means that all these sides are equal to 1 foot or 12 inches. So if I do 1 foot by 1 foot by 1 foot, that's really equal to 12 inches times 12 inches times 12 inches. And if you work that out in your calculator, 12 times 12 times 12, you do get 1,728. And it's going to be inches cubed because it was cubic. And so that tells me that 1 cubic foot, again, it's not equal to 12 cubic inches, it's equal to 1,728 cubic inches. So just be really careful with your conversions that use the word square or cubic. You have to figure out what that really means. So in this cubic problem, there are a whole lot more than just 12 tiny cubes that make up that whole 3D figure. There are 1,728 cubes inside that giant cube. All right, let's try interpreting a couple of these quantitative reasoning graphs. We've got 3 of these, and then we're done. Which graph represents decreasing distance with increasing time? So anytime I'm moving from left to right along the bottom axis, that's the x-axis, that's going to be increasing. So your smaller values are going to be over on the left and your larger values on the right. Same thing with the up and down axis. The smaller values are actually at the bottom. The larger values are up at the top. This is the y-axis. This is the x-axis. So if I want the distance to decrease as time goes on, that means my line is going to go down from left to right, because as time goes on means I move from the left to the right. Time is at the bottom. And so this graph right here shows me that I do have a decreasing distance. My distance was way up here, and as time goes on, that distance gets smaller and smaller as time gets bigger and bigger. So it would be this one right here. Use the information from the table to describe the relationship between musical frequency of notes and the beats in a tune. And I want to know how I can fill in these blanks. So the musical frequency of notes is decreasing between beat numbers blank and blank. So I'm just looking for where the second column in the table, the frequency, I'm looking for where those values are decreasing. So let's just take a look piece by piece and see if we can find that. 261.6, 392.0, that's an increase. And then between these two rows right here, it stays the same. These two rows, it increases. These two rows, it stays the same. And then the last two rows of the table, I am noticing that I go from 444 down to 392. That is a decrease. This is what I want, is a decrease. But I need to fill in the blanks appropriately. It's decreasing between beat numbers 6 and 7. That's how I would fill in the blank for this. It asks for the beat numbers. All right, and the very last example. Based on the graph, which statement could describe Janelle's trip home from school? So I'm always going to start by reading what the axes are standing for. That's going to help me determine which one's correct and which one's not. So it looks like my x-axis stands for the time in minutes, and the y-axis stands for her distance from her house in miles. So she's starting at whatever distance this is away from her house. And in this first chunk of the graph, her distance is getting smaller. That means she's getting closer to her house. Okay, so for this first piece, I'll highlight it in green. Her distance away from her home is getting smaller, so she's getting closer to home. And then the second little piece, the graph is flat. That means that time is going to keep going because I see movement on the graph from left to right. So time is going on, but she's not moving anywhere. She's not moving. And then the third piece, we'll just keep that orange. Her distance from home is decreasing again, but I notice that that line is not as steep. So she's still getting closer to home, but she's moving a little bit slower than that green piece. The green piece goes down a lot faster than this orange piece does. So she's still getting closer to home, but I'm going to write slow next to that one. And I'm going to write fast next to the green one because she's moving at two different speeds. Those lines aren't going at the same angle. So now let's see if we can find one of the options that matches what we just interpreted from those three pieces of the graph. So the first option says Janelle waited for the bus, rode the bus, and then walked home. Well, if she waits for the bus at the very beginning, that would mean that time is going on, but she's not moving. And that's not true. Our very first piece of the graph shows movement. So that first choice is going to be incorrect. She doesn't wait first. She's moving first. The second option, Janelle walked the opposite direction from home to the library, rode the bus, and then walked to a friend's house. Well, if she walks the opposite direction from home, that means her distance from home would be getting greater. She'd be getting further away from home. And that's not what we said with that green piece. We said at first she's getting closer to her house. She's not walking away from it. she's getting closer to her house at first. So right off, just from that very first bit right there, the opposite direction, that tells us that that one's incorrect. I don't even really have to read the rest of it. The third option says Janelle walked home at a constant speed. If her speed is the exact same everywhere, that means I have a perfectly straight line with no changes or bumps in it at all. And we saw 3 separate chunks to this graph, so I know that she's not walking at a constant speed. Let's make sure that this last option does make sense before we commit. It says Janelle rode the bus to the bus stop, talked with a friend, and then walked home. So let's see if that shows fast movement, waiting around, and then slower movement back to her house. If she rides the bus, that's probably going a whole lot faster than what I could walk. If she's talking with a friend, that means that she's not really going anywhere. She's just standing around talking. And then if she walks home, that would be a slower pace to get her back to her house. So this would be the description that fits the graph. This Unit 1 test has 16 questions, and it is available in Canvas right after Lesson 4. It should also be on your calendar. You get 2 attempts on it, so please use them wisely. Try the test once and see how you do. Go back and review the types of questions that you know you need some more help on, and please feel free to ask me for help before you try the test again.